Hello everybody. Today we're going to be taking a look at Lenz's law. Now the main idea of Lenz's law is that a changing magnetic field creates a current, and that current is in a loop of wire. If you just have a straight wire, there's not going to be an induced current, but if you have a loop of wire, by creating a changing magnetic field, you're going to create a current within that wire. Now, what are some ways that you can make a changing magnetic field? Well, you can make the field stronger or weaker. You can move a field quickly or slowly, or you can move a field towards or away from a loop of wire. The main idea with Lenz's law, though, is that the current will oppose the changing magnetic field. So let's take a look down at this example. We see that there is a loop of wire and there is a magnetic field that is pointing into the page, okay? In this example, we say the B field is increasing in strength. So what does that mean? That means that there's becoming more and more magnetic field lines going through this loop of wire. Now, Lenz's law says that the current will oppose the changing B field. So what does that look like? Well, in order to oppose that changing B field, this current is going to want to make a magnetic field that goes in the opposite direction to cancel out all of those new field lines that come into it. Well, in order to make a magnetic field pointing out of the page, we need to use our right-hand rule. So our fingers should be pointing in the direction of the created magnetic field, and our thumb will point in the direction of the current. So our thumb is pointing upwards, so that means that the current is going to go in this direction. Okay? So a changing magnetic field or an increasing strength magnetic field into the page is going to create a current that goes counterclockwise. Now let's take a look at some other examples here. In this example here, the B field is decreasing in strength. So what does that mean? It means that there's fewer and fewer of these magnetic field lines going through this current or this circle of wire. So if the B field is decreasing in strength, this current that is induced in the wire will want to increase the strength of the magnetic field. So it's going to try and put more into the page. Well, in order for the magnetic field to go into the page, your fingers point in the direction of the magnetic field, and your thumb is going to point in the direction of the induced current. So this is going to create a current that goes in the clockwise direction. Down here, the magnetic field is increasing in strength, but it's coming out of the page, okay? So if the magnetic field is increasing in strength, it's adding in more magnetic field lines. Well, in order to oppose that change, this current carrying wire is going to have to cancel those out by putting a current that cancels out the magnetic field coming out by putting one that goes into the page. Well, put your fingers in the direction of the magnetic field. Your thumb is going to point in the direction of the current. You should have a current that goes in the clockwise direction as well. The big thing to remember here is that the induced magnetic field will try to oppose the change, or the induced current will try to oppose the change in magnetic field, okay? And there's a cat. It's very cute. Let's take a look at these examples here. We have bar magnets, and they're moving into coils of wire here, okay? We're going to need to use another right-hand rule, which we're going to take a look at here in a second. The direction of motion of this bar magnet is going to be to the left, and if you remember a bar magnet, it's going to have a magnetic field that points into the South Pole, okay? If the direction of motion is this way, to the left, then this magnetic field here, it's going to be increasing in this direction. The magnetic field is going to increase in this direction. So the solenoid, or this coil of wire, is going to want to cancel that change. It's going to want to make a magnetic field that goes to the left. Well, in order to make a magnetic field that goes to the left, you have to point your thumb in the direction of the North Pole, and your fingers are going to curl in the direction of the current. In this case, our fingers will curl into the page or along the coil of wire. So the current is going to go up like this and wrap around. This is the induced current in this coil of wire. Down here, if we take the direction of motion to be the right, well, the magnetic field from the bar magnet is still going to be pointing to the left, but it's going to be getting smaller and smaller. So the change in magnetic field is going to be in that direction. Well, this coil of wire is going to want to keep the same magnetic field. So the magnetic field that this coil of wire is going to create is going to be in that direction to cancel out this change. So point your thumb in the direction of the North Pole. Your fingers are going to curl around in the direction of the current. So in that case, the current is going to be going up like this, okay? Which means it's going to be coming down through all of these wires over here. Okay? So that's Lenz's law in a nutshell from a purely descriptive standpoint point of view. But the big thing here is that nature hates change. Changing magnetic field creates a current in a loop of wire, and the current will oppose the changing magnetic field. Make sure to like, comment, and subscribe if you have any questions, and I'll see you guys in the next one.